So the DMA controller, it is a device which performs the transfer of data between the central processing unit and the peripheral devices. So DMA, we can say that it's a device which is usually acting as a peripheral device to the central processing unit, and this device can be programmed to perform a sequence of data transfer on behalf of the central processing unit. So if this is the CPU where we have the memory, and in memory the data is stored, and this is the peripheral device. Now this peripheral device, it wants to send some data to the central processing unit or to the memory, and the memory also it wants to send, or the central processing unit, it wants to send some data to peripheral device. So this transfer of data takes place through the DMA, that is the direct memory access controller. This DMA can be programmed, and through the softwares it can work, and it can transfer the data between the two devices. So this DMA, it is having a direct access to the memory, that is why it is known as the direct memory access controller. So this DMA, it is directly assessing the memory, and it is used to transfer the data from one memory location to another memory location, or from an input output device to the memory, or vice versa. Means the DMA can transfer the data between the memory also, that between different memory locations also it can transfer the data, and also it can transfer the data between an input output device and the memory, or from the memory to the input output device. Now, as the DMA it is transferring the data, so this direct memory access controller, or this 8257 IC, it has various channels which perform the transfer of data. So here I have written that DMA, it manages several DMA channels, and each of these channels can be programmed to perform a sequence of the DMA transfer. Means any type of transfer, it can be performed with the help of these DMA channels, and these DMA channels can be programmed in different modes. Okay. Now the direct memory access controller, the 8257 IC, it has 4 channels. Okay. It has channel 0, channel 1, 2 and 3. So these are the 4 channels through which the various types of DMA transfers or data transfer takes place. Okay. Now this was an introduction to the DMA controller. Now let's come to the pin diagram of the DMA controller. This is the pin diagram of the 8257 DMA controller. You can see that the DMA controller, it is a 40 pin IC. Here you can see the pins are starting from 1 to 40. All the pins with their pin names are given in this diagram. So this pin number 1 and 2, they have the signals IOR bar and IOW bar. These are the input output read and input output write signals. Now we have the third pin, we have MEMR bar and MEMW bar at the fourth pin. So these are the memory read and memory write signals. Then we have NC, which is, it means that it is not connected, means pin number 5, it has been left and any of the connections can be made at the pin number 5. Pin number 6 is the ready signal, and pin number 7, it is HLDA, means hold acknowledge. Pin number 8, it is ADSTB, means address strobe. Then pin number 9 is AEN, that is address enable. Then pin number 10, it is HRQ, hold request. 11th pin is CS bar, that is chip select signal. And 12th pin, it is CLK, the clock input. 13th pin, it is reset signal. 14th, 15th and 16th, this DACK, these are the DMA acknowledge signal for the channel number 2. As I have said that the DMA, it has 4 channels, channel 0, 1, 2 and 3. So we have the DMA acknowledge signal for channel number 2. This is the DMA acknowledge signal for channel 0. This is for channel 1 and this is for channel 3. So these are for channel 2nd and 3, and these two are the DMA acknowledge signal for channel 0 and 1. Then we have DREQ. These are the DMA request signal for channel 0, 1, 2 and 3. So these are the request signals of the 4 channels. Then at pin number 20, we have the ground VSS, and these DB7, DB6, DB5, DB4, 3, 2, 1, 0. These are the data bus, the 8 bits of the data bus represented by DB0 to DB7. Okay. This we have already studied that these are the DMA acknowledge signals for channel 0 and channel 1. Then we have VCC, which is the power supply connection, because power supply, it has plus 5 volts. So plus 5 volts are connected at VCC and ground is connected at pin number 20. Now pin number 32 and 33, these are, you can see A0, A1, A2, A3, A4, A5, A6 and A7. So these are the address lines. 8 address lines are there starting from A0 to A7. In between it, we have the 36 pin as EOP bar, which is the end of process signal. So these are the description of the names of the pins, 40 pins of the IC 8257 DMA controller. Now let us study each of the pins, that what these pins are describing, what are the functions of these pin signals. So first we will start with the VCC and the ground. VCC, it is the plus 5 volt power supply, and ground, it is the earth connection. So VCC, it is the plus 5. So these VCC and ground, these are the power supply connections. Next we have the CLK, that is the clock input, which is connected at the pin number. You can see here we have at pin number 12 the clock input. So CLK, its full form, it is clock input. Now this signal clock input, it is used to provide the clock pulse to the DMA controller. Now, as the 8257 DMA controller, it performs various types of operations like data transfer or any of the operation which is performed. That operation will be synchronized with the clock input. So, like at every clock input, this operation will be performed. So, this clock input signal, it is used to generate the timing signals which control the operations of the 8257 DMA controller. So this is providing the clock pulse to the 8257 DMA controller. Then next we have the CS bar, which is the chip select signal. Now this chip select signal, it is connected at pin number 11. You can see CS bar. So if any signal it is having a bar over it, it means that it's an active low signal. Means that this signal will be activated when its value is equal to 0, that is low. So this is an active low signal. It will be active when its value is 0. Now this chip select signal, it is used to select the IC8257. Whenever the microprocessor, it is connected with the DMA controller, then if the microprocessor wants to use the DMA controller, then it has to select that chip. Then only the DMA will operate, otherwise it will not be operated. So this chip select signal, it is basically used to select the chip of the 8257 DMA controller. So this chip select signal, it is used to enable the controller onto the data bus for CPU communication. Next signal we have is the reset signal. This signal, it is connected at here in this we have pin number 13 as the reset signal. So pin number this reset signal, it is used to reset, is this word reset, it means that we are initializing or bringing the system to its initial condition. And same this is in the case of this DMA controller. Here the reset signal, it clears out the contents of the controller, the contents of all the status registers, control register, all the registers will be cleared out, and the channels and all the system, it will be initialized to it, it will come to its initial conditions. Okay, so reset signal, we can say that So this reset signal, it is an active high signal and it clears the command register, status register, request and the temporary register. So all the contents which were present in these register, they will be cleared out and they will come to the 00 conditions. Okay, and this signal, it also resets the DMA by disabling all the channels. So all the channels, channel 0 to channel number 3, all the 4 channels, they will be disabled by this reset signal, or they will come to their initial conditions. Okay, they will be reset by this signal. Now next signal we have is the ready signal. When the microprocessor, it communicates with the peripheral devices, so the transfer of data takes place. Now there are some peripheral devices which are very fast in the communication, whereas the microprocessor, it is slow in its speed. So the transfer of data which is taking place, it is not synchronized, means the speed of the microprocessor, it is very slow, whereas the speed of the peripheral devices, it is very fast. So to synchronize the devices and the microprocessor so that they can easily communicate with each other, the ready signal is used. So when the microprocessor, it communicates with any of the peripheral device, it sends the signal to the peripheral devices for the communication. And when the peripheral devices, they are ready for the communications, they give out the signal ready. So this signal indicates the microprocessor that the peripheral device, it is ready for communication, it is ready for the transfer of data to it. Okay, so ready signal, it is basically a signal which is indicating that the peripheral device, it is ready for the communication. So this ready signal, it is an active high asynchronous input signal, and this signal makes the DMA controller ready by inserting the wait states. Now what are these wait states? Means when the microprocessor, because it is slow in speed, so it will be processing something while the peripheral device or the DMA, it is ready for communication. So the processor speed is very slow, DMA is very fast. So DMA has to wait for some time so that the microprocessor, it will finish its task and then it will start communicating with the DMA. So these are the wait states. This signal, ready signal, it will make the DMA ready for communication by inserting these wait states into the DMA, so that by the time the microprocessor gets ready, the DMA will wait for the communication. Okay, so this is the ready signal and the reset signals. Now next come the HLDA. This signal, it is the hold acknowledgement. And there is another one signal which is the hold request, which is known as HRQ. So these two signals, they are complementary to each other. Like we can say that when hold request is given, then in respect to it, the hold acknowledgement signal is generated. So first we will study the hold request, then we will come to the hold acknowledgement. Now the DMA, it works in two modes. First is the slave mode and one is the master mode. Now when the microprocessor, it wants to have the data transfer between the microprocessor and the peripheral device. So first the peripheral device, it will give a request to the DMA controller that it wants to transfer the data to the microprocessor, or it wants to communicate with the microprocessor. So when this request is received by the DMA, then the DMA, it requests the microprocessor that give the control of your buses to me so that I can transfer the data to the peripheral device. So it is asking, or it is making a request to the microprocessor that give me the control of your system buses. So we can say that this is the hold request that the DMA is sending to the microprocessor or the central processing unit, that hold your buses, tri-state the buses so that I can use the buses for the data transfer. So it is used to request the control of the system bus. And in the slave mode, this HRQ signal, it is connected to the DRQ input line, which is the DMA request input line. And in master mode, it is connected to the hold input of the CPU. Okay. So if we draw the diagram, here we have the CPU, then we have the DMA, and this is our input output device which wants to communicate with the CPU. Okay, so now this input output device, it will send a request to the DMA that I want to communicate with the CPU, and in respect to this, the DMA, it is going to send the HRQ to the CPU that give the control of the buses to me. So this will be connected to the DRQ input line of the DMA, which is here. DRQ DMA request will be generated, and in the master mode, it is connected to the hold input. By here we have the hold signal from the CPU, so it will be connected to the hold signal that I have relinquishes or relieved the control of my buses, and now the buses will be controlled by the DMA controller. So this is the hold request signal. Next, in response to this, the CPU, when it gets this request by the DMA, then in respect to this, it will send the signal HLDA that the request has been acknowledged by the CPU, and now the buses can be controlled by the DMA. So this is just an acknowledged signal in respect of this request. Okay. So this hold acknowledgement signal, it is in response to the hold request which is made by the input output devices and the DMA controller. So this HLDA hold acknowledgement, it's an active high signal from the central processing unit, and this signal indicates that the CPU has relinquished means released the control of the system buses, and the system buses includes the data bus, address bus, and the control bus of the CPU and the microprocessor. Okay, so when the DMA, it sends the request, then CPU, it gives the acknowledgement signal. Next we have the DMA request signal for each of the channels, DREQ 0 to DREQ 3. So we have 4 signals in the pin diagram. We can see that in pin diagram we have the 4 request signals, DREQ to DREQ 0. These are the 4 channels DMA request. Okay. So this signal DREQ DMA request, it is used by the peripheral device to obtain the service of the DMA controller. And the DMA controller, it is having the 4 channels, and these channels, they can work in the 2 modes, that is the master mode and the slave mode. Also there is it is having a type of mode which is known as the fixed priority mode. So in this fixed priority mode, the priority of all the channels, that which device will communicate first, because it is having 4 channels, so 4 input output devices can be connected. And which input device, suppose all the 4 input devices, they want to communicate with the microprocessor at the same time. Now which the microprocessor will communicate with which peripheral device first, so that priority is decided by the priority code. Okay, so in the fixed priority code, the channel number, this DREQ0, it has the highest priority, means channel 0 is having the highest priority. And DREQ3, it is having the lowest priority. Now polarity of this request, it is programmable. So this DREQ, we have given here the priority of the channels, that the DMA request by the channel number 0, it is having the highest priority, and DMA request by channel 3, it has the lowest priority. And the polarity of these DMA request, it is programmable, that is, it will have a positive polarity or negative polarity. Now then we have that the DMA request, it must be maintained until the corresponding acknowledgement signal, that is DACK, it goes active. Because every request, it will have an acknowledgement signal. So if suppose that the DREQ0, it has been generated, so this will be maintained until the acknowledgement signal for this has been received by the peripheral device. Okay, so in response to these DMA requests, it has the acknowledgement signals, which are the DACK 0 to DACK 3, which are the DMA acknowledgement signals. Okay, so these acknowledgement signals are used to indicate the peripheral devices that DMA has received the request of the data transfer. So these are the active low DMA acknowledged lines. Active low means that they are active when its value is 0. So these acknowledgement signals, they are used to notify or indicate the individual peripherals that the request has been acknowledged by the DMA, and now the DMA will send the request to the CPU to give the control of buses, so that the peripheral device can communicate with the microprocessor, or it can transfer the data which it wants to send to the microprocessor. Okay, Now these lines, they also act as the strobe lines for the requesting devices. Okay. Now next we have it was in respect of the DMA request which was generated. Next we have the lines, the DB0 to DB7, which is the data bus. So this data bus, it is a bidirectional three-state signals by state bidirectional signals are these. That means the data can be transferred in both the directions, and it is used to interface the system bus to the internal data bus. The internal data bus of the this DMA controller and the system buses, they can communicate with each other using this data bus lines. Okay. So this data bus, it is a bidirectional data bus. So it is going to send the data also and receive the data also. So the DMA, it is working in two modes. It's the slave mode and the master mode. So in the slave mode, this data bus, it is going to carry the command words, and in the master mode, it is going to send the higher bytes of the address to the 8257. So in slave mode, it is carrying the command words to the 8257 and status words from the 8257. So command words, they give the commands to the channels of the 8257, and status word, they give the information about the status of the channels and the request signals. Then we have in the master mode, because in master mode, the master is the CPU and the peripheral device will be the DMA. Okay. So in master mode, these lines are used. Used to send the higher byte of the generated address to the latch. So this was the 8 lines of the data bus DB0 to DB7. Then we have the signals IOR and IOW. First we will study IOR, which is the read input output. So this input output read signal, it's an active low bidirectional line. It's an active low signal, and this signal is used to load the contents of the data bus to the 8-bit mode register or the upper and lower byte of the 16-bit DMA address register or terminal count register. So it is loading the data into the input output devices. Okay. So this was the function of the IOR. Then we have input output write also. which is IOW. It's also an active low bidirectional input line. So this is an active low bidirectional line, and because DMA is working in two modes, so in slave mode, this line, it is an input signal which is used by the CPU to load the information into the 8257. So whatever data is there with the CPU is going to write that data into the 8257 during the slave mode using this signal. Okay, and in the master mode, this will be an output signal which is used by the 8257 to load the data to the peripheral. So in master mode, the whatever work was done by the CPU, that will be done by the DMA. So now DMA is going to load this data which is available with it to the peripheral device. Okay, so in slave mode, it is working as an input signal, whereas in master mode, it is working as an output signal. Next, we have the signal EOP, which is the end of process. This is also an active low signal. Now, when the data transfer is taking place between the DMA and the microprocessor and the peripheral device, then when the data is completely transferred, then this signal will be activated, which will indicate the microprocessor that all the data has been transferred, and now the other data transfer can be started up. Okay, so here we have. So this pin is providing the information that the DMA services has been completed. The data has been transferred between the peripheral device and the microprocessor. So this 8257 DMA controller, it allows an external signal to terminate an active DMA service by pulling the EOP signal low. So this end of process signal, it is indicating that the DMA services has completed, means if a data transfer has been started, so that when all the data has been transferred by the DMA, then this signal will be active, means it will be low, and that will indicate that the all the data has been transferred by the DMA. Now another way is that the 8257, it allows any of the external signal to terminate the DMA services. Suppose that the DMA, it is at present it is transferring some data, and there is an external signal which is giving this which is making this EOP signal low, means it is terminating the data transfer which is going on at that time. So that will be terminated and all the process will be stopped. Okay, so this line says that 8257, it allows an external signal to terminate an active DMA service by pulling the EOP signal low. Okay, so at any time the DMA services can be aborted by pulling the EOP signal low. So whenever the channels they are transferring the data, then a count is initialized. So this count is known as the terminal count. Okay, so when this terminal count has reached to 0, whenever the terminal count has been reached, then a pulse is generated by the 8257, and this pulse will make this EOP signal low, showing that the DMA service has been completed. So this was the EOP end of process signal. Next we have the A0 to A3 and A4 to A7. These are the address lines which are used by the DMA controller. Now A0 to A3, they carries the least significant address, that is the lower byte of the address, whereas the A4 to A7, they carries the most significant bits or the higher order address. Now their function, it is different in the master and the slave mode. In the slave mode, they are the inputs which are used by the 8257 DMA controller to address the control registers. And whereas in the master mode, they are the outputs which will give the lower order address uh, of the peripheral device. Okay. Next, we have the signal AEN. This is the address enable signal. This signal, it enables the 8-bit latch which is containing the address of the peripheral device. So this address enable signal, it is used to enable the 8-bit latch which is containing the upper 8 address bits, means higher order address it is containing, onto the system address bus. So this latch will be enabled when this signal is active. Now this signal can also be used to disable the other system bus drivers. They can also be disabled by using this signal. The next signal is ADSTB, which is the address strobe. So this address strobe signal, it is an active high signal and it is used to convert the higher byte of the memory address which is generated by the DMA into the latches. So the higher order address generated by the memory address register of the DMA controller, it is converted into the latches and it will be stored by this address strobe signal. Next we have MEMR and MEMW. These two signals are the memory read and memory write signals and active low signals. These are active low because they are having a bar over it. So this memory read signal, it is used to read the data from the selected memory location, and this memory write signal, it is used to write the data at the specific memory location which is being selected. Now we have the NC which is not connected, no connect. The pin number 5 of this DMA controller, it is not connected and it can be used to make a connection of any type whenever it is connected to any other devices, or it can also be used for the checking the continuity of the system. So in the pin diagram, we have were having all these signals we have discussed here. We have studied about all the pins here. Now let's come to the block diagram of the DMA controller. So this is the block diagram of DMA controller, which is showing all the blocks of the DMA. This is the data bus buffer, which is connected with the data bus of the microprocessor and the internal system bus. So this data bus buffer, it is connected to the internal bus, and this buffer contains the 8-bit data which is to be transferred. Then we have the read and write control logic. To this read and write control logic, the four lower order address lines are connected, A0 to A3, and we have the reset signal, clock, and input output read and write logics are connected. Then we have the chip select signal. So this chip select signal will decide that whether the chip is selected by the microprocessor, the communication will takes place or not. Okay, when this signal is active, then only the transfer of data will take place. Okay, otherwise the DMA will not work. Then we have the control logic and mode set register. Here the control word is stored and also the mode is decided. Here we have the higher order address lines from A4 to A7, then ready signal, hold request, hold acknowledged, and memory read, memory write, AEN, that is address enable, address strobe, and this is terminal count and mark. So these signals we have already studied in the pin diagram, that what these signals functions, what are the functions of these signals. Then these four are the 16-bit channels of the DMA controller. Here we have channel 0, this is channel 1, channel 2 and channel 3. These are the address and count registers of the channels they contain, which describes the address of that channel and the count which is loaded into the channel. Now each channel will have the DMA request and the DMA acknowledge signal associated with it. So DMA request will be given to the channel by the peripheral device, and DMA acknowledge is the acknowledgement signal given by the DMA to the peripheral device. So each channel will have the DMA request and the DMA acknowledge signals. Then we have the priority resolver, because there are 4 channels, so 4 input output devices can be connected, and which input output device will have the highest priority, it will be decided by this priority resolver block. Okay. Now, in this control logic and mode set register, we have studied all the signals except this TC, terminal count and mark. So let's see that what is the use of these two signals. So this terminal count, it indicates the present DMA cycle which is going on, that is whether the DMA it is working in the master mode or slave mode, and what operation it is presently it is operating. So that is indicated by the terminal count to the peripheral device which is connected with the DMA. Then we have mark. Now as the DMA it is transferring the data to the peripheral device, so this mark indicates that 128 bytes of data has been transferred by the DMA to the peripheral devices. So this mark signal, it will indicate that the current DMA cycle which is going on, it is the 128th cycle of the DMA, until the since the previous mark signal was sent. So when the mark signal after every 128 bytes of data, this mark signal will be generated. So the DMA will get to know that 120 bytes of data it has transferred. Then again it will start from first byte, then 1 to 28 it will transfer, then again the mark signal will be generated. So these terminal count and mark signals, they are used to indicate the cycle, the DMA cycles which is currently going on. So this is the block diagram and the pin diagram of the DMA controller 8257. So in this block diagram and pin diagram, we have studied all the pins and blocks of the 8257 direct memory access controller, which is also known as the DMA controller. So I hope that this topic is clear to you. Thank you.